Gnanam paramam dheyam. Knowledge is supreme.
Okay, so we start with our today's lecture. Till now we have seen various concepts of linear algebra, more of theoretical, though motivated by geometrical concepts. Today we are starting to look at a concept which is more dynamic in nature, and so to motivate that concept, let us look at a small video clip rather. Observe the movements of the objects in this clip. So, what are the kind of movements that you saw in this clip? These clouds were moving, these wings of the windmill, they were moving, the sun was moving, and this balloon was changing, and this flag was changing. Let us see it once again, some part of it, and observe the various movements. So, what are the various movements which are happening? Clouds were moving in certain direction, the sun was moving in along a particular path, the flag was shifting its position, and the balloon was becoming bigger or smaller. So, these are various things which we use in life, which we observe in our day to day life, and which have been used in this particular clip. So, let us see what are those things. So, movements were shown, and some of them were reflection, the flag changing, okay. Then scaling, balloon becoming bigger and bigger, retaining the shape, that is called scaling. Then there was rotation, the sun was moving along a circular path. How are these movements described mathematically? So, basically the idea is to look for maps, let us call it as a map T from R3, that is our word, okay, to R3, which preserve collinearity. What does collinearity mean? They take lines to straight lines, they do not change the straightness of 3 points. If 3 points are collinear to start with, then their images also remain collinear, right. So, lines go to lines. So, origin remains fixed in some of this, right. In translation, origin does not remain fixed, but in rotation, reflection, scaling, all these things, origin remains fixed. And third, the proportionality is maintained, the proportionality division ratios are maintained. If u and v, u, v and w are in a particular ratio, these points on a straight line were in a particular ratio, then the images also maintain the same ratio. So, question mathematically comes, what are the maps from R3 to R3 which have these three properties, which we observe in day to day life and which are useful. So, one can prove a theorem, will not prove that theorem, it is not very difficult, but we will assume it, that if T is a map from R3 to R3, then these two statements are equivalent. One, T preserves collinearity, division ratios and leaves origin fixed. Those are the transformations we want to look at. It says it is equivalent to saying the algebraic condition comes now. T of, you take two vectors v1 and v2 in R3, take their sum and take their image, that is same as the sum of the respective images. Okay. And if you scalar multiply a vector, magnify a vector, then the image gets magnified by the same scale. So, these are the two properties which are equivalent to saying if a map T from R3 to R3 will have these two properties. So, this is the algebraic version of geometry, right. We started with geometry, namely what are the maps which preserve collinearity, division ratios and leave origin fixed. This is the algebraic way of saying the same thing, an equivalent way of saying. So, this motivates the study of maps from vector spaces to vector spaces which have these two properties. So, we will note one thing important, that because T of alpha v1 is equal to alpha T v1 for all alpha, if I take alpha equal to 0, what does it give you? T of 0 is equal to 0. So, such maps will leave origin fixed, right. So, that is a consequence of this property, origin is fixed, T of 0 is 0, right. And note another thing, here it is from R3 to R3, but we will when I define for vector spaces, we will see that they need not be from same vector space to the same vector space, right. Domain and range need not be same. We will use this notation, and if V is contained in Rn is a vector space, we have defined the notion of a vector space, and U is inside V, which is also a vector space, then we will say U is a subspace of V, right. A subset also a vector space, we will call it as a subspace, and this dimension of a vector space we will write as dim bracket V, that will denote the dimension of the vector space. These are just notations, so that we do not have to write everything again and again. So, here is a formal definition of a linear transformation. V and W are vector spaces, T is a map from V to W. We say it is a linear transformation if T of the sum, image of the sum of vectors is equal to sum of the images, and scalar multiple of image of a scalar multiple is same scalar multiple of the image, right. If you add vectors, then the images can be added and that is same, okay. And if you scale a vector, magnify a vector, then the image gets magnified by the same scale. So, these two properties, okay. And one thing you should note here, you see this when you add V1 and V2, where are V1 and V2? They are in the domain, they are in the vector space V. So, you are adding V1 and V2 here, but T V1 and T V2 are in the image space W. So, there this addition is of vectors in W, right. So, here this addition is in the domain, here is in the codomain, okay. Keep that in mind, because here it could be R2, T may be R2 to R3 for example, okay. So, that is similarly here alpha V1 is scalar multiplication of the vectors in the domain, and that is in the image space. So, these are one observation you should note. So, here addition is in the domain, here is in the codomain, scalar multiplication in domain, and here is in the codomain. So, geometrically a linear transformation, as we said, preserves, right, it takes lines to lines, preserves ratios and leaves origin fixed. Algebraically, see algebraically what this essentially says is that there is a linear structure in the domain and this is a linear structure in the codomain. So, it gives due respect to the corresponding structures, right, in the domain as well as, that is algebraic meaning of that. And this phenomena comes in lot of branches in mathematics, whether you study group theory, here we are studying vector spaces. So, whenever there is a set and there is a structure and then one studies maps between those two structures, and if they preserve, those are the important aspects. That is what whole of mathematics is about, you take a set, look some structure on it, okay, you get an object and look maps between these objects. For example, in your calculus course you had the real line, right. On the real line, what is the structure? There is a notion of distance on the real line. So, notion of limits makes sense on the domain, closeness makes sense. You can take a range to be R or R2 or R3, there also is a notion of distance. So, closeness is there. So, you can study if something is close here, whether the images are close or not, continuity and such things. So, that is happens in most of the branches in mathematics. So, okay, let us go ahead with our concept of linear transformations. So, it is clear what is a linear transformation. Linear transformation is a map from one vector space to another, which gives due respect to linearity. That means, T of the sum, image of the sum is equal to sum of the images, and image of the scalar multiple is equal to scalar multiple of the image. So, these two, because on a vector space there is addition and there is scalar multiplication. So, these two are given due respect, that is a linear transformation. Let us look at this map R2 to R3. So, the map is T of x y, right. So, points in R2 R3 will, whenever we are writing as points, we will write as ordered pairs or ordered triplets. When we treat them as in terms of matrices, we will go as columns vectors, right. Keep that notation in mind. So, here we are treating R2 as ordered pairs, R3 as ordered triplets. So, for a point x y in R2, so x y in R2, what is the image? Image is 3 components. First component is x plus y, second is y, and third is x minus y, right. So, this is the map from R2 to R3. We want to know whether this is linear or not. Is this map linear or not? So, what we should look at? We should take 2 points x1, y1, x2, y2, take scalars alpha and beta, take a linear combination of them, alpha x1, y1 plus beta y1, y2, x1, x2. Look at the image, look at the images of the original points C of x1, y1, T of x2, y2, and take the linear combination, that two should be equal, then it will be a linear map, right. So, to verify this, let us look at T of alpha x1, y1 plus beta of x2, y2. These two vectors are added, right, with scalar multiples. T of that we want to compute. So, first what we do is we add these two vectors here anyway, right. So, if you add them, you will get alpha x1 plus beta x2, the first component, second component is alpha y1 plus. Now, T of that. So, what is T of a ordered pair? Add x and y components, y component remains as it is, x minus y. So, this first component alpha x1 plus beta x2 plus alpha y1 plus beta y2, that will be the first component, second remaining as it is. So, alpha y1 beta y2, that remains as it is, third difference of the two. So, that is the image of this, right. On the other hand, if you want to calculate, you can calculate alpha times T of x1 y1 plus beta times T of x2 y2. So, what will be that? So, this will be alpha times x1 y1, y1 x1 minus y1, right, that is the image of the first one, beta times image of the second. So, x2 y2, y2 x2 minus y2, and simplify, both will come out to be same. So, that is what it means by checking whether something is linear or not, right. So, take two vectors v1 and v2 in the domain, take a linear combination, take the image, take the images of the original vectors, take their linear combination by the same scalars, and two come out to be same. So, that is linearity. Okay, so, T is linear. Let us look at this. So, T of x y, it is from R2 to this is a typo here, this is R2 to R2, right. X y goes to x plus alpha comma y plus beta. So, x component you add alpha, y component you add beta. Question is it linear or not, right. Obviously, it is not linear, because in the linear, if T is linear, T of 0 should be 0. If I put x is equal to 0, y equal to 0, then it is alpha beta, So, alpha may be 0, beta may be 0, both may not be 0, one of them may be 0. So, if both are 0, then it is a linear transformation, but in that case what you are doing, nothing, it is an identity map, x y goes to x y. So, if either of alpha or beta is not 0, then this is not linear, right. And what is this basically? This is what is a translation. You are taking a vector and just translating the vector by a fixed vector alpha comma beta. So, translations in plane or even in R3 or in any Rn are not linear transformations, because they do not leave 0 fixed unless the translation by the trivial vector. So, this is called translation. So, keep in mind, translations are not linear. Whenever you want to check something is linear or not, the first thing you should check is whether T of 0 is 0 or not, right. That is a necessary condition. So, T linear implies T of 0 is 0. So, that is a necessary condition. So, always we want to check something is linear or not, first verify the necessary condition, right. That is how necessary conditions are used. So, it is not linear, okay. And this is of it causes some problem in computer graphics. See, we will show later on that these motions, translation, rotation, deflection, such things are used in computer animation, right. So, when you want to do computer animation, you have to tell the machine that at this point this line is to be rotated, like a robo is there standing and the arm moves, right. So, that means this is my center where I want to rotate and by how much angle I want to rotate. But how do I give a command to the computer? It does not understand rotate. So, all this is done via matrices. Okay. We will see how this command can be given by a matrix and then to a computer, and that computer does the job, right. So, that is possible, but the problem comes linear, this translation is not linear. That causes a problem, because to give a command to a computer we need to convert a linear transformation to a matrix, and linear and rotation translation is not linear. So, you cannot convert directly into a matrix. So, what is done is one introduces a dummy variable, right, and then converts this into, from R3 one goes to R4 actually, and then does it. So, you will learn these things if you are doing computer animation, computer graphics, you will learn there what are called projective coordinates. So, we will not go into that because idea is to introduce things. Okay. So, let us look at some particular ways of introducing linear transformation. Examples, they come from matrices. So, till now we have been treating matrices as collection of right rows and columns of numbers which help us to reduce right express linear equations as a system of linear equations and do various jobs. Here is a dynamic version of it. So, take a matrix of order m cross n. Okay. Consider the map T A. This A indicates that this map depends upon the matrix A. It is from R n to R m. So, keep in mind here matrix is of order m cross n. The map we are defining is from R n to R m. So, there is a switch. Okay. And how it is defined? For a vector u in R n, if u is a vector in R n, A is a matrix of order m cross n. So, you can multiply A with u, you can multiply A with u. So, m cross n, this vector is n cross 1, u as a column vector we are treated as column. So, what will be the result? M cross 1. So, that will be element in R m, clear. So, given a matrix of order m cross n, you take a vector u in R n and multiply as matrix multiplication, you will get a vector in R m. So, take a matrix, take a vector in R n, multiply, you get a vector in R m. So, this transformation we are writing it as T lower A, T indexed by A. It depends on the matrix A. Question is this a linear map? Right? Obviously, it is linear because we have observed the matrix multiplication distributes over addition. If you take vectors u1 and u2 and add them and multiply with the sum with the matrix A, is same as multiplying A with u1, adding it to A multiplied with u2. Similarly, scalar times, right. So, that property of matrix multiplications says that this is a linear. So, using the fact that matrix multiplication is distributive over matrix addition and commutes with scalar multiplication, right, it follows that T of A is a linear map. Is okay everybody? T of A is linear because A of A multiplied with u1 plus u2 is same as, because matrix multiplication it is A u1, A multiplied with u1 added to A multiplied with u2, and similarly scalar comes out. A alpha u is alpha times A u, right. Okay. So, this is linear. So, this is called the linear map induced by the matrix A. So, we give it a name. So, every matrix M cross n gives you a linear map from, not from Rm to Rn, but from Rn to Rm, okay, Rn to Rm. So, this keep that in mind. So, note A is M cross n, but T A is from Rn to Rm. Want to look at some particular cases of this. We will take a special matrix and see what is the effect happening. So, let us look at that. So, look at this matrix cos theta minus sin theta, cos theta, right. Theta is some angle between 0 to 2 pi. Let us take a vector x y in R2, right, and let us say that x is a point in R2, x y. So, polar coordinates. So, what are the polar coordinates? X is equal to r cos alpha, y is equal to r sin alpha, right. So, let us multiply this matrix by this vector and see what is the outcome. Okay. So, when you multiply T of x y, right, T of the image is the matrix multiplied by the vector. This vector is, right, what was x? X was r cos alpha, y is r sin alpha. So, when you put these values r cos alpha cos theta minus r sin alpha sin theta and put and use the trigonometric identities, what is this? R of cos theta plus alpha and this is r of sin theta plus alpha. So, what has happened? Earlier the point had polar coordinates r cos alpha, r sin alpha. Now, r remains the same, the distance of that image from origin remains the same, but the angle has changed to theta plus alpha, right. So, if r theta were the polar coordinates of the starting point, the image point has got polar coordinates r theta plus alpha, right. So, that means what? Geometrically it is a rotation by an angle theta, right. So, this matrix multiplication gives you rotation by an angle theta, depending on theta positive or negative, clockwise or anti-clockwise. Okay. Right. So, let us look at one more. So, this is rotation by an angle theta. Let us look at this 1 0 0 minus 1. So, if I take a vector x y and multiply by this, what will happen? 1 0 0 minus 1 multiplied by x y. So, what will be the image? X y minus y, right. X will remain as x, but y changes to minus y. So, a point x y has changed to x minus y. So, what does geometrically look like? X coordinates remain the same, the y which was there, it has become minus y. So, this is what is reflection against the x axis, y goes to minus y. So, it is reflection against x axis, right. And similarly, if you look at minus 1 0 0 1, that give you reflection against the y axis. So, reflections they are obtained by this simple matrix transformation in the plane, right. So, I will come across many more slowly. I just wanted to introduce two of them. So, rotation has been done, reflection has been done. Okay. We will look at examples more a bit later. So, now here is, so linear transformations become important from these two examples anyway, right. They are the transformations which help us to represent rotations and reflections at least. Now, here is an important theorem which says if T is a linear transformation from V to W, and let us fix a basis of the domain, that is V. So, V1, V2, Vn is a basis, and not only it is a basis, we have fixed that the order of the vectors which are appearing in that as a set, that also is fixed. We fix the order also, right. So, V will remain as the first one always, we will not shift the position of V1 to V2 or anything. So, such things are called ordered basis, right. You take a basis and fix the order in which the vectors in the basis are going to be written, okay. That is called an ordered basis. So, what does basis of V mean? What is the meaning of saying that something is a basis of vector space V? Every vector in V is a linear combination of the basis elements. Not only it is a linear combination, it is a unique representation. If a vector V is written as sigma alpha I V I, then those alpha i's are unique. You can't have more than one representation because of independence, if you recall. That is what the importance of independence was. Generates and independent, everything should be a linear combination and unique representation should be there. So, we are fixing a ordered basis V1, V2, Vn. Then the claim is T is uniquely determined by the values on these n vectors V1, V2, Vn. That means, T is a linear transformation on a vector space V. If we fix its values on basis elements, then its value for every vector is fixed. That means, to determine a linear transformation completely on a vector space of dimension say n, there is a n elements in the basis, you need to know only the values on the basis elements. Where does this basis vector go? That is all, nothing more is required. So, let us see why that is so. So, let us look at any vector V. By definition, we have got a basis V1, V2, Vn. So, every vector must be a linear combination, so and unique one. So, V is a unique linear combination of V1, V2, Vn. That means, V is a linear combination. That means, what? V is equal to alpha 1 V1 plus alpha 2 V2 plus dot 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 alpha n Vn, and these scalars alpha 1, alpha 2, alpha n depend on V, but they are unique for V. You cannot have two choices for any one of them. There is only one choice for representing V as a linear combination, that is uniqueness. But if T is this, so what is T of V? T of V is T of the linear combination, but T is linear. So, what is T of the linear combination? It is a linear combination of the individual ones. So, T of V is T of the sum, sigma linear combination, which is same as sigma alpha I T of V I by linearity of T, right. Now, if these T i's are fixed, T of V i's are fixed, right. We have said, and only choice is alpha i's, right. If you know the values of T V i's, alpha i's are fixed, then this value is fixed now, right, because given a vector V, alpha i's are fixed, right, there is unique choice, and if we know T of V i's, we know T of V, right. So, once you fix the values of a linear transformation on the basis vectors, its value for every vector is fixed. There is only unique way you can do it, right, and that is here, that if V is sigma alpha I V I, then T of V is sigma alpha I of T linear combination of T V i's. So, if T V i's are fixed, alpha i's are unique for the vector V, so everything is fixed, right. So, this equation specifies that unique value for T of V in terms of the values T V1, T V2, once you fix them. So, this is very important. We say that to know value of t on any vector in the vector space, you have to know only the values on the basis elements, right. That is what is important, right.